Okay, so this lecture is over this concept of what's known as dipole moment, which is basically a measure of the charge separation in the molecule. And so basically it's just a measure of how polar a molecule is as a whole. So how do you measure dipole moment experimentally? You would have a setup like this. So a couple of metal plates hooked up to a battery, but the battery, so if the battery is not connected yet, so let's say you had HCl molecules, which is a gas, and they were inside that chamber between the two plates, so the gas molecules would be orientated randomly because they're just floating around. And then when you connect the battery, what's going to happen is one of the plates is going to become charged positive and one plate will become charged negative. And so how does that work? Because the electrons will leave one of the plate and go through the battery and be deposited onto the other plate. So one plate becomes positive, one plate becomes negative. And so now would you still expect the HCl molecules to be orientated randomly? And the answer is no, they are not. Because if you remember, HCl is a polar molecule. It has polar covalent bonds. So where the hydrogen is partial positive and chlorine is partial negative, because chlorine is more electronegative, then hydrogen. So chlorine is going to become partial negative and hydrogen partial positive, so now they'll be attracted to the plate. So CO will be attracted to the positive and hydrogen attracted to the negative plate. So the molecules would become orientated with respect to the plate. And then if we did the same thing for H2 molecules, so in H2 molecules is a gas as well, so they would be orientated randomly. And then when you hooked up the plate, would you expect H2 molecules to be orientated with the plate? And the answer is no, because H2 is nonpolar covalent. So no atoms partial positive or partial negative, so nothing's going to be attracted to the plate. So the H2 molecules will still be random. And so what you do now in this experiment is unhook the battery and measure how long does it take for the plates to lose their charge. So at some point, if you unhook the battery, then how does the negative get from the, how do the electrons get from the negative plate to the positive plate, because they can't go through the battery anymore? Well, so they would go through the medium, and in which case the medium is HCl in this case, and H2 in this case. And so since H2 molecules are not attracted to the plate, they're basically going to act as an insulator. Whereas the HCl molecules would act more like a conductor because they're very polar. So this plates will lose charge separation the fastest. And that's basically a measure of dipole, what's known as dipole moment. So experimentally what this is, if you're measuring how long two plates can maintain their charge in physics, that's what's known as capacitance. And if you take physics 2, electricity and magnetism, you'll probably study capacitance at some point. So we're not going to be doing any experiments like that and making any measurements on dipole moment. You just have to understand what the concept is. So how do we represent dipole moment? So an HCl being a polar molecule, H is partial positive, chlorine is partial negative. So the electrons are going to be pulled from hydrogen to chlorine, and so that's a symbol for dipole moment, is to use an arrow with a dagger at the end, and the arrow goes from partial positive to the partial negative atom. So the unit of dipole moment is what's known as the debye. So 1 debye is equal to 3.34 times 10 to the minus 30 coulombs times meters. But again, we're not going to do any calculations with the dipole moment. You have to basically just know what a dipole moment is, and you have to know how to predict direction of net dipole moment. So if we take a molecule, so HCl has a dipole of 1.08 dipole, which is a pretty large dipole moment. HCl is a pretty polar molecule. Whereas a molecule like H2, no partial positive, partial negative, so it has 0 dipole moment. So it's a non-polar molecule. How about a molecule like CO2? So it's a linear molecule, and so is anything partial positive, partial negative? And the answer is yes. Oxygen atoms are partial negative because they're more electronegative than carbon, and the carbon atom's partial positive. So if you draw your arrow from positive to negative, so there's a dipole like that and a dipole like that, those are what are called bond dipoles. And then if you add the two together, in this case, they cancel. So I like to think of it like playing tug of war. If the two oxygens are stronger than carbon and they both started pulling on the rope, then which way is the carbon going to move? And the answer would be not at all, because the two oxygens are equal in strength, so they're just going to cancel each other out. So it's like two forces in opposite directions, they cancel each other out, so there's no net dipole moment. So CO2 has polar bonds, right? They're polar covalent, but it has no net dipole moment. So it's a non-polar molecule as a whole. Okay, how about water? So if we had water, drew a Lewis structure, and assign partial charges, hydrogen's partial positive, oxygen's partial negative. So if we drew our arrow from negative to positive, so that would be bond dipoles. So does water have a net dipole moment? Well, if H2O was linear, then it would have no net dipole moment, but of course we covered when we talked about VSEPR model and sp3 hybridization, water is not a linear molecule, it's a bent molecule. And so in order to predict dipole moment, you need to know the structure, three-dimensional structure of a molecule, so that you know what the net directions of each bond dipole is. So since it's not linear, since it's bent, then it's pulling electron density like this. So so that would be the two bond dipoles. Do they cancel each other out? And the answer is no, they do not cancel each other out. And so I like to think of this like, if you've had physics before, if we take each of these and put them on a Cartesian coordinate system at the origin, and if you think of them like forces, since those are two forces in equal but opposite, well not opposite directions, but they're equal in magnitude. So if you add the two together, then what is the net direction? So I like to think of it like this. This has a plus 1/2 x component and a plus 1/2 y component. And this has a negative half x component and a positive half y component. So the two X components cancel because one's half positive and half negative, but the two Y components are both half positive, so they would add together. So the net dipole moment would be in that direction. So if a water has a net dipole moment in that direction. And it has a pretty large dipole moment as well. Yeah, 1.94 dipole. So water has polar bonds. Each OH bond is polar, and it's a net dipole. So it's a polar molecule also. Okay, couple more examples. So what about BF3? So fluorine's more electronegative than boron. So each fluorine's partial negative. Boron's partial positive, so each fluorine pulls electrons towards itself. Right. And so because of the symmetry of the molecules, so this fluorine pulls that direction, this fluorine pulls that direction, and this fluorine pulls that direction. If you ignore the top one for a minute and just focused on these two, then they would have a net in that direction right between them, which is exactly opposite direction as this one. So they cancel each other out. So it has no net dipole moment. If one of these was a chlorine instead of a fluorine, so if this was not a chlorine or fluorine, if this was a chlorine instead, well, chlorine's more electronegative than boron also. So it's pulling that way, so it's pulling up, and the two fluorines are pulling this way, so they're pulling down. But the two fluorines are more electronegative than the chlorines, so if you add the two fluorines together, then this is bigger than this. So the net dipole moment would be in that direction. Since these two forces pulling down is greater than this one force pulling up, then the net dipole moment would be straight down. Okay, so what about a molecule like CCl4? So a molecule like CCl4. Okay, so chlorine's more electronegative than carbon, so each of the chlorines partial negative. Carbon's partial positive, so this chlorine's pulling electron density that way, this one's pulling that way, this one's pulling that way, and this one's pulling that way. So all the bond dipoles look like that. And then so if we just ignore this one on top for a minute, so these three chlorines, since they're all pulling down, they're going to have a net dipole moment right in the middle of them straight down, and that's exactly opposite the direction of this one. So these three chlorines together would cancel out the dipole moment of that one. So this molecule has no net dipole moment. All right, and as far as the X components would cancel, so this has an X component and a negative Y component, and this two negative X components would cancel that X component out, and then all of these have a negative Y component, which would be straight down, and that would cancel this one's positive Y component out, and these two Z components would cancel each other out. Okay, so if this molecule was not symmetrical like that, so instead of a chlorine here, for example, if you had a hydrogen here, so a molecule like that, well then carbon's more electronegative than hydrogen, so this is pulling electrons that way, and these chlorines are pulling electron density that way. So carbon's pulling electron density this way off of hydrogen, and each of the chlorines is pulling electron density that way. So this would have a net dipole moment, and it would be straight down between all of the chlorines. Okay, so basically what you just have to do with respect to dipole moment is if you're given a molecule, just predict what the direction of the net dipole moment would be.